Yeah, many thanks for inviting me to this nice meeting. Really, I really learned a lot. I was not part of that uh, group of scientists who really developed DFT. I'm too old, so I came into the 90s, as I will outline in a moment. So, yeah, so I learned that in particular that this heavy resistance of the quantum chemistry community against DFT, and also what Kirian said, that this is so similar today to the machine learning, to the advent of machine learning. We really should think carefully about it so that the young people could still work and make their own developments and decisions. So this is my view on this. So yeah, the natural choice for large systems, this is definitely clear. There's no need to explain this. And what I'm going to talk a bit about is the non-experts. So large systems and non-experts, that mean essentially that a biochemist without much experience should be able to run a computation in the foreseeable future, right? I don't think that it is possible today. And we should, in my opinion, work on this. Okay, so I will say a few words about my first contact with DFT. Yeah, then this was a great introduction by Erin about the importance of dispersion corrections for large systems. The asymptotic limit should be right. So I will add some points from my side. Yeah, then I will talk a moment about robustness, what it actually means. So everybody seems to know what it is, but we need to quantify it, or open ways to quantify this. And we developed or are working on so-called mindless molecule generation and the benchmarking, nice collaboration together with Paola from Microsoft. I think this will also have a benefit, in my opinion, for the machine learning community, we hope. But you can also learn a lot about our functionals. And then something that has not been taught so much here in this conference, I'm a bit surprised, is about the speed. So in my opinion, all the DFT calculations we are doing are way too slow. So if you think about biochemistry, then the typical biological system is, say, 500 to 1,000 atoms. This is a typical cutout of a protein that you may simulate if you want to add a drug, computed drug protein complex. So, and then you have to run many calculations, maybe not MD, but many conformers you have to sample. So these are thousands or 10,000, maybe millions of calculations. So the limit is maybe 1 second or so, CPU seconds per energy on gradient evaluation. And I don't think that any of the existing DFT methods can do this. But we should aim for that, because this would mean really DFT in biology. And so I think the only way to do so is going back, so to semi-empirical theories. And I will spend the last minutes or so on what I'm developing since 2 years or so. So I'm hoping to get DFT accuracy at tight binding speed. Okay, so that was my first contact with DFT. In a way, I worked in Bonn on hydrocarbons, aromatic ones and strain bonds, and then I came across this interesting molecule. You may know it, azolane. It's an interesting hydrocarbon. It's small. It has a low-lying excited state. It's blue. It has a relatively big dipole moment for hydrocarbon. And interestingly, if you run the calculations in those days at 92, 93 or so, with Hartree-Fock calculations, then you get this structure here with a bond alternating CS symmetry. And this is actually wrong according to X-ray measurements. The correct structure is delocalized C to V. And I wrote here the SCF method, so Hartree-Fock fails to predict the correct minimum. And then I run multi-reference CI and MP2. It took weeks and so on and so forth, getting the right structure. So that was actually a correlation problem, a left-right correlation problem in the pi system, as you may, which I found out. And then Nick Handy was in the institute maybe the same year or a year later or so. And I asked him, can DFT compute the right structure of azulene? And he said, oh, of course, yes, it can. He was absolutely sure. And, yeah, really? Are you really sure? I mean, I spent so many weeks and months on that calculation. Yeah, and indeed, as I found out a few months or maybe a year later, when the first Togomol code, including DFT, arrived with a quick B-lib calculation, it turned out that he was right. DFT, even with a simple function, GGA gives the right structure and everything right. And I was immediately converted to it. So that was my my change basically from the wave function world to the DFT world. And I think it was a good decision. Yeah, my first topic is the large molecule problem. So we have seen some of these papers cited by Erin already. Pavel Hopsa, Peter Pulai, Axel Becke noticed in the mid-90s that something is wrong with DFT, not with DFT in itself, but with the functionals that we are using. So there are basically no van der Waals minima for prototypical systems. And actually, if you go to the literature, this was in a way known. This is maybe the first DFTD paper that I found, 74. This is a kind of LDA, at least as far as I understand it. And already 50 years ago or so, that was dispersion corrected as we do it today. Around the same time in the 70s, this was already noticed by Reinhard Aris and Scholes for Hartree-Fock, that you can easily repair this dispersion problem that appears in all good mean field theories because the long-range correlations are neglected. Yeah, this is often said, and I heard it already here, that this is something weak. I mean, this is true if you count this on an atom pairwise basis, but for a review, I made this comparison. So just for the chemists to get a baseline value to say, I put 2 point charges at 10 Bohr distance, 5 angstroms, and then this is roughly 60 kcal interaction energy. And then I try to construct a similar system just by dispersion. So I put 100 light HCNO atoms at the center of mass distance, also of 10 Bohrs. And then you have 100 atoms here and 100 here. This is 10,000 interaction pairs, each with a dispersion coefficient of 10, divided by 10 to the 6, because the distance dependence is 10 to the 6. And this is then also 60 kcal. So yes, on a pairwise basis, the dispersion is weak, but not in realistic systems, because it adds up. It's always attractive. And in the big systems, we are naturally interested in as DFT people, it really matters. And then interestingly, together with Peter Schreiner, published here, we found a chemical system where this 60 kcal coincidentally showed really up. So this is this interesting example of the hexaphenyl ethane, which is in the unsubstituted version not stable because of too much steric repulsion here between the phenyl group. So this is a chemically bound system. So this is not long-range van der Waals something. And then interestingly, if you add the tertiary butyl groups, so if you add more steric bulk, more steric strain, then surprisingly this molecule can be synthesized. Actually, you can measure the dissociation energy, you can measure an X-ray. So getting more steric bulk, bigger substituents, you improve binding. And this is essentially a result of the dispersion between the tertiary butyl groups. And in the DFTD methods, the nice feature of them is that you can switch it on and off the dispersion. This is the full potential energy curve of that system. Here's a van der Waals minimum, and here's a secondary covalent minimum. And you switch off the dispersion just by the tertiary butyl groups, everything moves to the unbound regime. So this is a chemical system where the covalent bonding is really driven by dispersion. So just saying that it is weak, be careful. It's weak on a pairwise basis. So this can be considered as a kind of intermolecular case, but actually the intramolecular dispersion case is, in my opinion, equally important. And this is the case, I mean, when you change the shape of a molecule. And for chemists, the most relevant situation is protein folding. And this is a simple example here. This is a folding, unfolding coordinate, reaction coordinate between this unfolded state and this folded one of a polypeptide or small polypeptide chain. And we have here the black curve is here coupled cluster reference data. So the unfolded one in the gas phase state is less stable than the folded one. This is set to 0 here. Now you can apply various density functions and various dispersion corrections. For example, uncorrected B3LYP is qualitatively wrong. So the unfolded state is more stable than the folded one, which is incorrect. And the incorrectness comes from the missing of the dispersion or the over-repulsiveness. So if you now apply various dispersion corrections, then you more or less close to the coupled cluster reference. I also want to note here that some of the D'Andrula functionals, which make not explicit dispersion corrections, but implicit corrections by the parametrization, which are asymptotically incorrect, they underbind here. So they are below the truths. So the correct asymptotics in the dispersion energy form of the potential already matters here for relatively short and small systems. So if the system has 1,000 atoms or so, that is even much more relevant. So dispersion is also important in intramolecular situation. And Irin just told you that we now have more or less solved this problem. We have many versions of dispersion corrections around, D1 to D4, Kachenko-Scheffler, Beckett-Johnson, and so on. They more or less perform the same and have this general structure is pairwise and then maybe many body expansion. So it's often said this is an empirical correction. I really don't like it because this is on really solid grounds. We have 3 basic approximations. It's a many or multi-body expansion, it's a perturbation expansion, and a multiple expansion that you see basically here. The most empirical term here is the damping function because you have to connect this, because it's a correlation contribution, you have to connect this to the short-range correlation piece. Just there's no way out. But this damping function normally contains only a few parameters. The good methods determine as Irin said, these dispersion coefficients kind of ab initio, either by XDM or by TDDFT as we do. So yeah, there is some empirical element in these methods, but I think this is on very solid ground and has the same level of empiricism as the normal function nodes that we apply. Okay, and then that leads me already to my next topic, so thermochemistry and benchmarking. So this is a slide that is roughly 10 years old or so. At that time, we had this GMTKN30 database. Axel gave yesterday a good introduction into that. What you now, with such a database that covers a large part of chemistry, what you now can show several things. So one goal was to check if Jacob's ladder metaphoric picture really holds. Is it just a dream or something like this, or is it scientific reality? The second point is, what is the effect of thermochemistry in this, of the dispersion on thermochemistry? And what you see here is in red, not dispersion corrected, in green dispersion corrected, always an average over various functionals in that class. So it's just one LDA, of course, but some GGAs, some meta-GGAs, some hybrids, and some double hybrids. And you see, first of all, yeah, Jacob's ladder is absolutely true. So each rung of the ladder, you basically improve without dispersion corrections and with dispersion correction. The second thing to learn here is that the effect of on thermochemistry is really huge. So going from 7 to 5 means essentially one step on Jacob's ladder just by adding a dispersion correction. To be fair, I should say that this thermochemistry database has a lot of non-covalent interactions and conformational energies which are sensitive. But it's something across the board of chemistry. So therefore, this is not unreasonable. What is also interesting here to see is that at both levels, B3LYP is slightly worse than the average hybrid. So there we are not using, or many of us, or many in the community are not using the best hybrid. So which is, has something to do with our conservative minds, but yeah, anyway, this is an observation. So now we extended this database, so the actual one is GMTKN 55. Sorry that I turned it around here, so this is just differently ordered, and I kicked out the double hybrids, and in this graph you have some various functionals, here range separated hybrids or hybrids, meta GGAs, GGAs, and again you see Jacob's ladder holes. What is added here is a new class of methods, so rather common base functionals in reduced versions, so-called composite DFT methods. Basically, we compromise in the basis set, make it smaller, and try to correct for the deficiencies by simple, often pairwise corrections. It's mainly the basis set superposition error that you have to correct for. These methods employ double zeta or triple zeta basis sets and are typically 10 to 100 times faster than the parent methods in the big quadruple zeta basis sets. Yeah, and you see we will lose little accuracy. For example, if you compare here ArtoScan 3C with the parent here, this is just almost nothing. It's basically on par with the parent, with a saving of a factor of 20 to 30 or so in the normal applications. So this is one good thing to know. We can do more or less the same level of accuracy DFT at much reduced cost. And the other thing to learn is that there's still a huge gap in accuracy to methods that we would like to use. So semi-empirical methods or tight binding methods, which are at least a factor of 100 times faster, maybe a factor of 1,000 or so, they are here way off. This goes here through the roof. So the dream would be, from that slide, what you can take with you is that the target would be around 10 or so. 10 weighted total mean absolute deviation 2 is a very reasonable for in very, very many applications. So this would be the dream for the next generation tight binding method. I will later come to that point back. So before doing so, I want to say a word about this benchmarking. So this is a huge database, so roughly 1,500 reactions across all chemistry, excluding transition metals, which are known as another story. But the question is here: is the choice of the systems of the reaction, is this really representative of chemistry? Or the other question is does a good result here means that something like omega B97 MV from Martin, is that really a robust function? I mean, it performs well here, but does it perform robustly in general? And I think this is an important question, because we want to explore the unknown, not the known is boring. So some years ago, we had this idea of so-called mindless benchmarking. John said this is not a good choice for a name. The other name would be artificial molecule benchmarking, something like this. But I think mindless is the more catchy title. And you see already here, I put this word robustness in quotes because, I mean, this is not so well defined. But maybe we can, by doing benchmarking in this way, without chemical bias, and this is the idea, we can do it. I can do it better. So we worked on this. It was forgotten for some time, but very recently with this tight binding development, we revisited this, and my student Marcel just wrote and also uploaded it to GitHub a brand new Python implementation of this mindless molecule generator, so you can use it. It's very easy. Basically, you need an Orca and an XTB, which runs the quantum chemistry to generate molecules that look like this. They basically can have arbitrary composition. Our main requirement is that they are more or less single reference. They can be unusual by any chemical standard, but they should be a single reference so that our DFT calculations as well as the coupled cluster calculations are reasonable. The coupled cluster calculation at the end of the day as a reference is the difficult part. So the generation is rather easy and straightforward. You can generate on your laptop computer 100 in a few hours or so, and then you may check if they really satisfy your conditions. So this is very easy input. You can really give a detailed atomic composition. You can take elements from across all chemistry, including the actinides and lanthanides. We recently implemented also them. So I'm generating also actinide mindless molecules with this approach. Yeah, and now, we already had in the GMTKN 55, there was already this version here. At that time, the coupled cluster calculations were really expensive, so we limit this to relatively small molecules. We later extended this then, and then you can take just this subset from GMTKN 55 for these mindless molecules to check if the functionals that we are using daily are really robust or not. What we are doing here is the following. What to benchmark now, so you have this molecule, we set up a chemical reaction that is reasonable and that is not atomization. We don't want to put an emphasis on the open shell nature of the atoms. In principle, you could also compute atomization energies, but we prefer here to hydrogenate the mindless molecule to the small closed shell fragments, so that any bias by the open shell nature of the atoms that this disappears, and also this lowers the reaction energies so that the numbers are not so big. The typical reaction energy in a mindless molecule with 10 to 20 atoms is a few hundred kcal or so. Okay, so we're talking about large numbers, but not too large. And then you see here mean absolute errors in kcal. So if the reaction energy is 300 or so, this here means this is a 10% error. Reasonable, I would say. And you see also that for this mindless benchmark, more or less Jacob's ladder holds. So you can take the average over all the functionals in each class, or you can always take the best one, and you will find it roughly follows Jacob's ladder, which is interesting in itself. So this holds for, Jacob's ladder seem to hold for any chemistry in a way. There are also interesting observations. First, this composite method, R2scan3c, really stands out because, I mean, for reasons that we don't really understand at this point, it's actually better than many of the hybrids. Although it never has seen in the parametrization any of these mindless molecules. This is something that we need to understand. The other things to note is that functionals that are highly parameterized, like MN15 and other Truller functionals, are not doing so well, while old-fashioned hybrids, here this one is also from Don Truller, with only 6 parameters, perform also very well. Yeah, so you can look in detail into that. What is also interesting to note that the double hybrids are in a way for these molecules, which are more or less closed shell, also relatively robust. So there's no breakdown by the inclusion of the perturbation correlation in these systems. Yeah, this is just short note on how we do this. So you basically generate a random list of atoms, and then are the coordinates generated. Basically, we contract all the randomly placed coordinate atoms coordinate together. Then there's a tight binding geometry optimization performed, and only if something survived this, we make further checks. You can also do simple DFT checks if there's for the gap and the SDF convergence to check if this is a reasonable thing to include. Yeah, and then we were with this new generator, we were able to get a bigger set. Now mindless molecules reloaded with about 300 molecules, mindless molecules. I should say this is up to chlorine. So for heavier elements, we have to work a bit more on the reference couple cluster correlation, energy, semi-core, core correlation, and so on and so forth, to make the reference better. But here the reference here is really close to the limit. And even with this new mindless molecule benchmark set, you see again Artoscan 3C is on par with many of the hybrids, which is really surprising. But I also find interesting here that Martin's omega B97 MV is also very good and actually better than the XV. It's not here, it is much better than the XV, the precursor. So that was then one of the reasons to choose for further developments of the tight binding method omega B97 MV. So this is then later, for the later part of my talk, my reference. I believe in MV and hope that any of my tight binding developments will get this right. Yeah, also here you can note that some of the Dont-Ruler functionals are not so robust. Some are. So MO6, it's for whatever reason better, I don't know. So I think these molecules, mindless molecules, are really useful. Of course, 300 is not enough for mindless for machine learning, but for benchmarking quantum chemistry and tight binding, for example, this is a very, very useful procedure. Okay. So now I'm coming to the end. So I said already that for interesting systems in particular in biochemistry, we have to perform very, very many calculations normally. So the typical screening approaches work with much more, hundreds of thousands of systems. And the standard DFT is way too slow. Also for large systems here in biochemistry, this is simply not doable. So we need something much faster. So I think semi-empirical quantum chemistry still has some right to exist. Although it may be replaced at the end of the day in the future by some machine learning, but one should keep in mind that the actual machine learning potentials are kind of force fields, okay? In their current state, they do not consider any electrons. So it's a sophisticated force field, while this is quantum intrinsically. So we treat at least the valence electrons quantum mechanically. They are there, and we also have all the properties that are associated with the electrons. So there is still an advantage of doing quantum mechanical treatments. So we are working since about 8-9 years or so in tight binding theory. It is a well-developed theory by Harris, Focus, Seifert, Frauenheim, Elsner in Germany. So there is this DFTB, and we jumped in 2015, 2017 by developing what is now called GFN1 and GFN2 XTB, which are tight binding methods in the spirit of DFTB. The main difference to the DFTB method was the strategy for parametrization. So from the very beginning, we're aiming at the full periodic table by avoiding all pairwise terms. So this is just very conventionally only atom-wise parametrization. So each element gets it, whatever, 10, 20, 30 parameters or so. but in a very conservative way. So I'm always trying to save parameters, not to add more than there should be. So the old tight binding methods had some issues, and that we wanted to repair in this new version. They all have a good foundation here in this tight binding energy expression. This is really a density functional theory. It's not, the energy is not a functional of the density, but it's a functional of the fluctuations of the density around the reference density. And this reference density is normally a superposition of neutral atom densities. So we can save a lot of all the computations of integrals by taking the free atom as a reference state and only looking at the fluctuations relative to that state. And that saves all the comp time. So there are some issues with that theory. It's nice, it's well developed, but it misses some terms. And one of the terms that you're missing when you just apply this straightforwardly is the Fock exchange. So what you get out here normally, so all DFTB and GFN2, 1, 2, is all basically GGA level. So you have the same problems that GGA have. So artificial charge transfer, gaps are too small, and so on and so forth. So here in that, we now really add Fock exchange and the Mulliken approximation in a range-separated way. So we want to approximate omega B97 MV, and we are also adding the right Fock exchange as an omega B97 MV. So this is the first new main ingredient in that method. The other problem in that method is that you have to expand these fluctuations here in a basis set. So you're actually using the same or similar basis set in a normal DFT. And to save time, you normally use minimal basis sets, and these minimal basis sets are normally really bad. So I thought we have to improve here at the very beginning. So what I developed independently was an adaptive basis set. So this basis set is different for every atom in that specific molecule. It's actually specific for each atom in that molecule. So the contraction coefficients in that basis set depend linearly on the effective charge of the atom in that molecule. And therefore the name of that is Q valence single zeta with some polarization function. This is the best basis set I can think of for almost the best basis set for a minimal basis set method. Yeah, this is just a crude, brief picture of what we did. This is here in equations, so it's as usual, we have an electronic energy, the repulsion of the reference atoms, the dispersion energy, and then in different orders of this expansion, you have an extended Hückel type term, electrostatics in various orders, and this is new here. The first order electrostatics, that had been a term that has been forgotten in a way before. We have to correct for the missing polarization functions to keep the speed, and this is the new range-separated Fock exchange. So empiricism is basically the same as before, and I think this, at least for this cost level, this is the best physics that I can put into a semi-empirical theory. Yeah, we lose some efficiency, roughly 50% compared to GFN2 by the additional matrix multiplications by the Fock exchange, but it's not much. So 50% is absolutely acceptable. Our gaps are really good. So we almost have range-separated hybrid DFT gaps. Okay, a few results. We have seen this mindless molecule 311. These are really, really difficult thermochemistry for a semi-empirical method. You see our competitors here, or our previous versions, which have MADs of a few hundred kcal instead of 10 or 20. This is the same figure. Now I put in here the GXDB, which is the name for it. It's slightly worse than the best functionals we have in a big basis set. But note, it's about 1,000 or 10,000 times faster. So it's on par with DFT, with bad DFT, I should say, not with the best DFT. But yeah, this, I think 30 or 40 here, this is really impressive. What is very important in chemistry are reaction barriers. Our previous methods are basically GGAs. So this is a test set from Gino Di Labio, 449 barrier heights forward and reverse and reaction energy. This is our previous GFN2 in blue. You see errors for barrier of around 10 kcal is not good. This is not really acceptable. This is kind of reference here, B3 over PD4 QZ. Actually, we are better than B3 in a huge basis. Because we effectively have more Fock exchange, right? So this is a range-separated hybrid, like Martin's functionals, which also perform well in this 3C flavor. So now this is GMTKN55. I promised you our target is something of roughly DFT level. This was the graph that you have seen before in a different version. This is what we had. This is composite DFT at various levels, and you see we are almost there for a factor of, depends, 1,000 to 10,000 or so. Okay, geometry is also good. I have no time. Let's summarize. Yeah, it's, I hope, hopefully 20 years after my first DFTD paper, it's clear that we need them to really go to the large molecule regime. Empirically, we have seen that Jacob-Seder holds for extended thermochemistry benchmark sets. And I think that there are various density functional approximations that perform really robustly for this mindless chemistry. And I think that I would better controlled way of doing empiricism, that this is absolutely acceptable, even if you go for robustness. Why R2 stand 3C stands out so clearly in that zoo of low-cost metal? I don't know. We have to look more in detail into that. And I think we have now something that is really useful for many applications. Yeah, my main co-workers in that project, Marcel, Thomas, and Andreas. Most of our stuff is available freely. Yeah, thanks for your attention.
Thank you very much for that inspiring talk. So,
yeah, so Stefan, very exciting work. So I wanted to ask you about this mindless benchmark. So you said that it's for now only like the main group. Yeah, so I mean, just about the transition metals, because comparing them to like having the reference with the hydrides, like I think they're not all that single reference.
I mean, you can generate any composition.
Yeah.
Up to element 103, Lorentzian. But getting them the good reference is another story. How to get a reliable reference for a 3D mindless transition metal complex is really a good question. At this point, I'm using the molecules that survive this process with the omega B97 MV as a reference for my tight binding. My tight binding can't be better than that DFT. So I'm happy if it matches the DFT. If that DFT is right or not, or how good it is, I'm not asking. This is another question that, of course, one has to investigate. But there we need better than couple cluster single reference methods. So got Monte Carlo, we tried. This is maybe a way to go. Definitely, this is absolutely important. But the generator is there. We know a lot about the functionals. You can make them now more difficult if you wish, or you can keep them as single reference as they are. I mean, many transition methods also can you get many single reference type ones, right? They are not necessarily difficult. It depends so much on the.
Okay. Yep.
I was curious about the speed up. You presented it as if it's more like a prefactor speed up, but is it a speed up also in terms of the scaling?
No, it's a diagonalization bottleneck.
Okay. Yeah. All right.
More? Yep.
Very, very nice results. Can I ask you about the mindless benchmarking, following up on Susie's question, which is how do you, what criteria do you use to exclude systems that you think might be strongly correlated? And do you make any effort to sort of distinguish easy cases from moderately easy, less easy cases?
Not yet. So our criteria are SCF convergence, so number of cycles in tight binding and DFT and gap. But you can add any of the standard criteria as additional selectors. It's just a single point after the generation.
Yes,
Okay.
orbital instability might be a
Yeah.
good one.
Anything.
Okay, let me ask you, if early DFT hadn't failed to do dispersion, we would have known much less about dispersion than we know today.
Yeah, right.
So this is this is what we learned.
Absolutely. Yeah.
Yeah. So we should be grateful for that.
In a way, we learned. You're totally right. We learned a lot by this failure. 100% agree.
Okay, unless there's some very urgent, are you been already? We'll take lunch. Okay.